Hey guys, my name is Benson, and today I'm going to present our work, Disco Efficient Distributed Window Aggregation. So what is window aggregation and why do we need it? So window aggregation is used in data streaming to analyze a bounded subset of data. So say we want to have the average stock price of the last 10 minutes. And why is the current state of the art problematic? So just imagine a smart home setting where we have multiple homes all producing data at different locations. And they send all this data, the raw data through network hops to a central cloud data center where the data is analyzed. We can see here that we have redundant raw data transfer because we're just keeping on sending between the hops, and we have unused compute resources in the network hops. So to solve this, we propose Disco. And Disco is a distributed window aggregation approach where we push down the computation of the windows and the aggregation down to the network hops. So we can utilize their compute resources, and after that we only need to transfer aggregate data instead of raw data to reduce the data transfer. So how does this work? Let's quickly look at Disco's architecture. The Disco consists of three main components: the child nodes, the intermediate nodes, and the root node. You can see here in the first step, the child nodes that interact directly with the sensors receive raw events. They then create the windows and perform the aggregation on this data. And then they pass on the aggregate to the intermediate nodes. The intermediate nodes then collect all these partial aggregates from the children, merge this data, and pass the merged aggregate again to the root node. The root node then has collected all data from all children, merges it, and then can, in the last step and the fourth step, produce the final aggregate. So when we're speaking about this window merging, what exactly are we merging? We can see here windows on two different nodes. Same colored windows represent the same logical window. And we can see here that window one starts and ends, for example, at the same time on both nodes. And the window merger can then use this information to actually align the windows and merge the correct result. And a quick evaluation at the end, we're looking at scalability here of the average function. We can see that our approach scales linearly with the number of nodes, because each child node produces windows and aggregates independently of each other, whereas in the central approach, it all happens on a single node, which is the bottleneck. And also for network costs, we can see that our approach, as we only have to send the partial aggregates, reduces the network cost drastically compared to the centralized approach, where with an increasing network tree height, we always have to see the redundant raw data transfer. And just to finish off, there are a few links to our paper, poster, and code. And thank you very much for listening to our presentation.